like that
do
face.
that though.
Why not? It's
I don't
fine.
know.
Hey,
But
let's say
He can
okay.
do it. He
It's
can do
kind
it.
of cute though.
But the those are the bad guys.
They are the
But
bad
it's
guys.
still kind of
evil.
cute.
I like
It's
that.
like, don't you feel bad for Gollum? I mean,
No.
Not really.
no.
Why on earth would you feel bad for Gollum?
He fell into a pit of lava.
Where did Gollum come into this?
Don't worry then. He what?
After trying to kill and betray everyone,
kind of
and
like
he thought it was coming to him.
No,
Wasn't his fault.
he was so
Goddamn
He's
Frank.
a recovering
excited
addict.
he had it back that
He was so greedy.
Come on.
No, he fell in it. That's his fault.
Greed doesn't mean death.
Okay,
Greed
well.
means death.
Okay, it can though.
Here is
Betrayal and
the
attempted
equivalent
murder
of
does.
what we've been talking about. Believe it,
I like the other one better.
believe it or not.
I'm ready to leave.
I believe it, but I like the other one better.
So, how does this relate to the water power analogy? Well, we have a supply of power. Okay, that's the battery in this case. It has a positive and a negative side. And you know what happens when you connect one to the other, right? You short circuit, right? And it might heat up and blow up on you. But anyway, it's a supply of power. Now that is comes down the circuit this way, and this is, it's not exactly the same, but it's sort of like a faucet. It's a little device, it's called a resistor, that only allows electricity to flow at a particular rate. So this is 10 ohms would be a very low value. So it doesn't do much, but it does prevent the battery from just blasting itself through. So some electricity goes through here, some comes out of here, however you want to put it, and it goes into another bucket. This bucket is very similar to the battery. It's this one. It's a capacitor. It is also a power supply, except that unlike the battery, it can be discharged very quickly. When you short circuit a capacitor, it goes boom, disappears. A battery, on the other hand, will discharge itself slowly. It'll give you a lot of power for a long time. The capacitor, short time. So capacitors are characterized sort of like buckets would be. How much volume can they hold? And eventually, from how high you drop them. The higher you drop them, the bigger the impact, right? And so capacitors are characterized also a plus side and a negative side. And they're characterized in terms of their volume, in terms of farads. Mr. Farad from I don't know where gave his name to the unit of electrical energy or storage, whatever it is. And a typical handgun, the kind that you slip onto a flat with a camera, maybe this big, has a capacitor that's about 1,000 microfarads. That's millions of farads. A farad, if you were to have a capacitor that was 1 farad in size, it would be pretty big, maybe as big as this card here. So you're dealing with millions of farads, although this is 1,000 millions. Nevertheless, it's a fairly small capacitor. Now it's big enough to kill you, but it's in terms of a farad, it's small. And it's characterized by how many volts it can be charged up to. And that depends on what you have over here. So if the battery here is a 300 volt battery, you want to put a capacitor here that can stand 300 volts. If it's a capacitor that can only stand 100 volts, in that case when the charge on here gets to be 100 volts, and you raise it some more, eventually the capacitor explodes. It says, I can't handle that. So you want to match the voltage capacity or level to which the capacitor can go to that of the power supply. It could be 300 volts, 500, whatever it is. You want to match the two. If this is higher than that, that's okay. This being lower, that's no good. So anyway, now if you were to take a voltmeter and you measure the voltage here, and you measure the voltage there, eventually, as you let the capacitor fill up, you'll read 300 volts, because that's what the battery is also. So now, what do you do with the positive and negative? Well, the negative goes over here, and it goes into this. Typically, it goes into a glass tube, but it doesn't have to. It could just be there in air. And the other side, okay, goes to here, and it goes to here. Now, assume that there is no glass tube there. What you could do is you could take these two wires and connect them together. And what happens then? Well, that's when you short circuit this. This says, I have my positive connected to my negative, and I go from 300 volts to nothing. And at the same time, I warm up these wires. But you don't do that. Typically, in a handgun, the steady state situation is set up inside of this glass tube. It is filled with, typically it is xenon gas, but it could be argon, it could be neon, it could be other types of what's called rare earth gases, inert, as they sit there. It means that, I don't know what inert means, but to me it means it's just sitting around. The gas in there, though, or the distance between the two ends, these two wires, is such that electricity can't flow from here to here. If it did, you'd have a lightning flash. It would be the same as with the bucket falling off because you have exceeded the rating of this gap. That means that the gap has some electrical characteristic that says you can raise the voltage from here to here, okay, to 20 volts, it's okay. 50 volts, it's okay. 100 volts, it's okay. 300 volts, it's okay. But you start to go, oh, in this case, you could raise it to 1,000 volts, I think. You know, I'll have to check on the logic on this. And still nothing happens. Okay. Well, you still only have 30 volts, 300 volts. But if you go beyond 1,000 volts, there's going to be a lightning bolt that goes from here to there. There'll be a self-discharge. And this is when you have overfilled the bucket. Okay. But this will withstand 1,000 volts. You're only operating at 300. That's with the gas just being itself. It's a little inert cell. And now there's something else in the circuit. Well, one other thing you notice, your shutter sync contact, or the camera sync contacts. I mean, that is going to determine when this thing is going to do its thing. So what does this control? Well, there are two takeoff resistors, just like that one, except they're much bigger. Notice this is 1 megohm, this is 1 million ohms, and that's just 10. Another 1 million ohm resistor here. These are like, I'm not sure what they're like. I was going to say they're like weirs that conduct water, but in this case, notice that you are actually connecting the negative side to the positive side, which should cause a short circuit, right? But it doesn't, because the values are so high that the short circuit that is there hardly leaks off any of this charge. However, if you measure the voltage between here and here, you'd notice that it is 1/2 of what it is from there to there. This kind of an arrangement is called a voltage divider. Now you can change the values of these, make this one big and make this one smaller, and then you can alter what the reading is going to be from here to here. Typically it'll be 1/2, so these two are exactly the same. Now why else do you want them there? Because they're safety resistors, they protect you. Notice the camera is connected, you know, right to the plus, and it's also connected to the minus. Oh, that's not good. Because when you close it, then it's supposed to short circuit, but it doesn't. Because the amount of charge that goes through here is very small. There's some, but small. So if you touch this, or you touch here, nothing happens. Or yeah, actually, just by touching here, nothing happens either. So these are safety resistors, and they're also voltage dividers. Notice there's another little capacitor here. Now this one is a lot smaller than that one. What is it? 10,000 times smaller, right? Puny little capacitor. Now, whereas this one charges to 300 volts. This one over here, notice that the negative side goes to negative, the positive goes to the positive. It charges to half of 300, so 150 volts. And the negative side of it goes through a coil to connect to the negative. Next to this coil, there's another coil. Notice this has a lot more turns than this one does. This kind of an arrangement is called a transformer. And when these are bigger than those, in that case this amplifies things. But it only works when there's a change. Okay? If it's a steady state situation, it doesn't do anything. So this can deal with alternating current. So if you AC going through here, there'll be AC coming out of here, and it'll be as many times higher in value as the number of turns on this side are than the ones on that side. So if this is 10 times as big, in that case, if you read here 150 volts, this will be 1500 volts. But this is a DC circuit. I mean, it's direct current. There's no alternating thing. So what good is this? As it is, nothing. Nothing at all. Except for the fact that you can make a change happen. How do you make a change happen? Well, you short circuit that capacitor. How do you do it? Well, you connect the plus side through your camera shutter contacts to the negative side, also through the coil. And when you do that, you discharge this capacitor. It goes from 150 volts to 0. That's a change. This transformer says, hey, I detect the change. It dropped from 150 to 0. So over here, in sympathy, in reverse, I'll put out a spike that's 10 times bigger than this spike was. So I'll put out 1500 volts out of here. Not for a long time, just enough time for the dummy to release the rope. And where is that rope? Well, the rope is right in here. This gas can withstand 1,000 volts when it's just sitting there. However, when it is tickled, when it's ionized, it changes from atoms to ions, charged particles. Not all over the place, but somewhere near where this wire comes in. When some of the gas is ionized, the breakdown voltage inside of this tube drops from 1,000 volts to 100 volts. Well, that's all you need. Because if this, under the ionized state, can only stand 100 volts, and you're giving it 300, there's going to be a breakdown here. And this is going to short circuit. There's going to be a lightning bolt that goes from here to here. And when you get the lightning bolt, you get the light, and you get the heat. And that's how an electronic flash works. Now, there are a whole bunch of other things that are attached to electronic flashes, but the basic premise or circuit is this one. Harold Edgerton is famous for electronic flashes, and he has a book called Electronic Flash Stroke. First couple of pages, unbeknownst to me, but then as I checked, he had this drawing. It didn't quite look like this, but if you look at it, it's the same thing. So now what else can we do with an electronic flash? So anyway, as far as electronic flashes, the burst of light that you get out here, and I think I mentioned, the glass tube is a frill, an addition. You don't actually need that. You could just have a spark in air, and that's what we're going to use tomorrow. So no tube, but this wire would still come close to between these two. And the ionization that would happen is of the air between the two electrodes. So the air by itself is going to resist a spark going across. But when you take some of the molecules of air between them and you ionize them, now the breakdown voltage drops below the supply voltage and boom, you get your flash. So one of the things that we want to kind of get an appreciation for is how do you describe the duration and the power of an electronic flash? Power essentially says, you know, I can use, the more the power, I can use a slower sensor speed or whatever, a smaller aperture, and that's under certain conditions desirable. Or I can compare one flash to another one in terms of power. And that power is typically expressed in watt seconds or in joules. And it's dependent, okay, the energy is dependent on two things. The volume, essentially, of the capacitor, how many farads it can hold, or microfarads, and the voltage to which you raise, to which that capacitor is raised, divided by 2. So if we want to get more power, we can do one of two things. We can increase the capacitance, that makes the capacitors bigger and bigger and bigger, or we can keep them this small size and raise the voltage. Raising the voltage is the more effective thing to do, because if you double the voltage, you quadruple the power. The problem is that as you keep raising the voltage, your flash starts to become more and more dangerous. There have been many photographers, and I don't think that I'm exaggerating, that have been killed by electronic flashes. Probably not because the voltage in the flashes was too high, but because it was too high for the environment in which the flashes operated. You operate in a very humid situation, or again, someplace where it was not designed for you to work with, 1,000-volt capacitors. All of a sudden, you might get a tingle. It could be deadly. So there's practical limits to which you can raise the voltage. And if that's not good enough, then once you reach that, then increase the capacitance. Well, now your flash gets bigger and bigger and bigger. And, however, there is another factor associated with flashes, and that is duration. How long will the flash last? And this is described by this little relationship, roughly speaking. In this case, notice the capacitance is still a factor. And there's another factor, which is R, which is resistance. That means the opposition of the circuit to allow electricity to flow through the various components. Because believe it or not, even though you might have a copper wire going from here to here, that copper wire doesn't allow electricity to flow through it except at some maximum rate. After that, it starts to heat up and eventually it melts. So, but you have to measure this value at the time that the flash is working. And it's not an easy thing to do. However, it's resistance while the flash is operating, or the gas is ionized, essentially discharging. Capacitance, again, could be microfarads, and duration in that case is in microseconds. So you say, okay, well, how do I get short durations? Well, lower the resistance. Lowering the resistance, again, has a practical limit. You can't make it 0. And lowering the resistance means it's more expensive. So there are practical lower limits to this. So then what's your other alternative to get short duration? Well, make the capacitance smaller. But what happens if you make the capacitance smaller in terms of power?
Power goes down.
Power goes down. So duration and power at opposite extremes of desirability. You can't have power and short duration at the same time. Essentially what I mean, if you have some power, and at some point you can't get any shorter duration because you can't make this smaller. And at the other end, you can't get more power by increasing the voltage because it becomes deadly. So, and this I think could be computed if you had some figures, and I believe that in a couple of slides we do. But the main point of mentioning this is the fact that duration and power don't go along together. Short duration. It's a matter of compromise. So, how do you then determine what the duration of a flash is? You'd like a flash, any source of light, to go from zero output to 100%, remain there for a while, and then drop to zero in no time. Well, there are not too many things that operate that way. That would be a square wave output. And flashes are by no means square wave. Their output looks kind of like this. When you tell them to turn off, you ionize the gas and the capacitor discharges. They don't have much trouble going from 0 to 100% output in very little time. It'd be 10 millionths of a second or so. They're as high as they'll get. But almost immediately they turn around and they start to decay in output. And they decay, and they decay, and they decay, and they decay, and then eventually photons cease to exit. So then you say, okay, well, what's the duration? Is it from the time that the first photon came out until the last photon left? Probably not. Because once you're in this region here, I'm exaggerating as to how far I'm going, the output of the flash is so low that you're not going to detect it. Right? So at that point it's useless. Well, durations are determined from the time that the flash reaches half of its maximum output until it comes back and reaches half of its maximum output again. And all the light that's produced over here is neglected. So this is called half peak to half peak duration measurement, which is that much. Even though light keeps coming out of it for that much. So this is a standard way of determining the duration of electronic flash. But it's a fairly optimistic characterization of a flash, because it says, at this point, if you think about this, at this point, your photograph is underexposed by one stop, right? 50% output. But you know that if you underexpose 2 stops, whether film or digital, it doesn't matter, you still can use that light. 2 stops under exposure is not bad. Even 3 stops under exposure is not bad, especially for highlights, right? So you could measure from, that would be quarter peak, okay, or to 1/8 peak, but no, the standard is half peak to half peak. Why do you think that is? Any business majors here, or anybody interested in business, marketing?
Smaller number.
That's right. Smaller numbers in duration terms for electronic flashes sell. So an honest manufacturer, in terms of describing what their flash unit does, might say, well, you know, my flash lasts this long at 10% output. Another one says, oh, my flash lasts that long. The two could be exactly the same. But because one number is shorter than the other, some people are going to prefer the shorter number. So what happens is that nobody is honest and says, you know, I'll measure my duration at 10%. They all go for this. because it's a shorter number. But this is useful output of the flash, and it's a much more accurate way of determining or characterizing what the duration of a flash is, particularly going to 10%. I mean, this is 1 stop, 2 stops, 3 stops. I mean, that's not bad. So, but how do we make a calculation of time using the figures that we have? Capacitance, resistance, and voltage. So here's our capacitor. It's a 1,000 microfarad capacitor. Well, that's right here. It's in microfarads. So, and our voltage is 300 volts. If you do that calculation there, out comes 45 watt seconds. 3 times 3 is 9. Okay, so we have a 9 over here divided by 2. That's 4, 4.5. And then there's some multiplier, right? I think I did that eventually. One day I did it. There it is, 45 watt seconds. Now what about the duration of this flash? Well, we have the capacitance, we have a resistance, and for resistance, this assumes a fairly conservative value, low value, 4 ohms. That's pretty low. Now we still have our 1,000 microfarad capacitor, and you work this out, and it turns out to be 2.8 milliseconds or something like that, a 350th of a second. This is typical of the little handguns that you put on a camera. There are ways to make that resistance smaller. I think I said this before. But it costs money. There are superconductors, materials that allow electricity to flow better than just plain old copper. But they're not cheap, so manufacturers don't use them if they don't have to. So there's your typical handgun. And you might think that the duration on those flashes is very short. It used to be, you know, we said electronic flashes are 1,000th of a second. No, typically they're not. They're quite a bit longer, even a half peak. And then they could be even longer than that. And studio flashes, I'm not sure if any of you use the big, whatever they are upstairs in the studios. What are they, Broncolors and others, when you use them at full power, and we'll talk about partial power shortly. If you photograph somebody who blinks, you know, eyelids will be blurry. So the durations are pretty long. Lots of light, you know, for a long time. So what can we do to shorten the duration? Well, we can do, what we can do is interrupt the energy going to the flash tube after a while. Now, there are two things that are going to be shown here. One of them is you can make the flash automatic to say that, well, once I've reached a particular light level or collected a certain amount of light, I will turn the flash off. Now, this is done by putting up a switch here, which is, it's called a thyristor switch. They're no longer that new, but they're devices that can switch themselves open on command. And the command comes from a photocell that's looking at your scene. So, and it's a resistor, and and there's a little battery here, and it's coupled, or it takes it from the main, and it's coupled to a small capacitor. And when the small capacitor reaches a particular voltage, then the switch opens. So the light goes from here to your subject, bounces back to the light meter essentially, and when the meter says, oh, I've reached a particular voltage here, I'll open the switch. You can imagine the closer the subject is, the faster the switch opens, because the earlier that it collects the amount of light that it needs. So that way you can bias this, you know, you start out with more or less, depending on what sensor speed you have. Or you can do something else, make this a fixed resistor, make this a variable resistor by hand, and that's built into some flashes, like in the 283 here. This is a variable power control, and it says when you have discharged so much energy, stop and don't waste what you got. Just keep it in the capacitor, but stop making light at a particular point. So you can bias the circuit, saying, well, when half of it has been expended, stop, or when a quarter of it, an eighth, and so on. Well, what does that do? Well, take a look at the output curve for the flash. Flash wants to do the same thing every time. So it does this, goes up to there, and goes down to there. However, with the switching system, what you can say is, go up to there, come down to here, and when you get to this level again, open the switch. So you waste, well, you don't waste, you don't use this amount of energy which is stored in your capacitor. Okay? And notice also that, well, in this case the duration doesn't change much, but the tail end jams up that way. And when you are at quarter power, in that case you switch off here, and so on. So this time gets shorter and shorter. However, you also get less light. Again, I'm pointing out the fact that it's a matter of compromise. You don't get, oh wow, you don't get much for nothing. So, but this is the whole concept behind partial power electronic flashes. You can use this, some of the studio strobes have it too, and you get shorter durations, lower power. Sometimes in a studio situation you can fire 4 or 5 heads at the same time, and that doesn't give you much less light, but still the duration shortens up. So one other thing I want to say, no, I have a gazillion things to say, but I'm going to pick on just one. That's a joke. Anyway, you know, artists, society as a society, we've been influenced by artists for how long? From how long?
Ever.
Excellent. That's right. Ever since the Neanderthals and stuff, we started drawing on caves. Yeah, artists have influenced how we see things or perceive them. And this would indicate a particular situation. It indicates some object that's traveling from left to right, indicated by these lines here, or so we presume. Actually, there's no fact that supports that. Artists just felt, oh, we'll put these lines here, and then that is supposed to indicate that it's going that way. Well, let me show you what an electronic flash photograph of a bullet in flight looks like. The bullet is moving that way. Forget the display. Look at it. The blur is on the side that the bullet is going towards, not on the side that it came from. Right? Now, how can that be? What's the explanation?
Whenever the flash fires, it's at full power, so it's receiving the most exposure at that time. But as the bullet continues to move, and the flash is dropping off, like shown in that chart, it's receiving less exposure.
That's right. And the highlights disappear last, right? The highlights trace on longer than the shadows do. That's right. That's it. That's what you were going to say too, right?
Yeah.
I know, right? Yeah. So this is kind of disconcerting. Photographing with electronic flashes. And there's really no way to get around this, other than to devise some circuit that doesn't produce so much afterglow. And sparks in air, such as we will use tomorrow, have that more of that characteristic of cutting off more quickly. Otherwise, for commercial situations and so on, when you use studio strobes and you see something like this happen, the only recourse that you really have is to use a short exposure time. to cut into the output of the flash. And focal plane shutters tend not to be too good at that. I'm not sure about digital ones. So anyway, here's the situation. And 15 minutes. And I guess you'll have to live with the demo on the board. So again, the experiment here, or the point here, is that you want to photograph a balloon blowing up. Why you want to photograph a balloon blowing up, I have no idea. But if you know how to photograph a balloon blowing up, you can do a lot of other things, because the same problems that you run into with this are going to be associated with something that might be more sophisticated. So we got this balloon. And a couple of people get together and say, okay, well, you push the button and I'll pop the balloon. And I think you realize that they're going to have some trouble, right? And the chances of getting a picture of the breaking balloon are going to be governed by a couple of things. One is being...
sheer dumb luck.
Yeah, very good. And the other, if you want a sharp picture, is going to be...
mechanics of the shutter being fast enough.
exposure time, right? So you got to first of all have a quick-acting shutter so that it lasts a lot less than the duration of the burst itself. And then you have to operate the shutter so that it happens to catch the balloon at the time that happens. Well, I bet you that even if that pin goes into here and the person pushes the button, are synchronized, synchronization is the word, I guess, the likelihood of you catching it is pretty slim, because the cameras don't respond fast enough. If you tell them, make the picture, they wait a while. Even if they wait a hundredth of a second, it's too long. So you say, oh, I need some help. I'm going to take a synchronized, sound synchronizer, something that detects sound and closes a switch. Well, that's what the camera needs to operate, right? You push the button or close the switch. So you take the sound sync, connect it to the switch, pop the balloon. It still doesn't work. It doesn't work, again, because the camera takes time to operate. So you get a faster acting camera. Or do what?
Keep the camera on all the time.
Yeah. And then
Fire the flash with the sound.
take the sound sync and fire a flash. Because this has zero I want to say zero, but very short reaction time. When you tell it to fire, boom, it's up there. Okay? Within a few millionths of a second. The camera shutter is open at the time, then you capture it by the light of the flash, and you get a picture. Now, there's, however, something else to keep in mind. That is, where is this microphone in relation to the place where you push the pin?
Gotta be close.
There. You want it as close as you can to catch the very beginning of the break. Because if this is removed, a few feet, by the time you hear it, it's already gone. Right? And it would be useful in that case to know how much later a photograph is taken than another one, assuming that you start out with the microphone, let's say, 6 inches away. Okay, and now you're going to move it away. You say, well, how much later is the next picture going to be because you moved the microphone away? That will depend on something. What do you think? Speed of sound. You know what the speed of sound is?
1,200 feet per second.
1,200. Who said that?
And
Yeah, about 1,100, 1,200. But 1,200 is kind of an odd number, right? I like to just call it 1,000 feet a second. But where did that come from? Where did you learn that?
I know that speed of sound is 343 meters per second.
Well, but again, that's just a fact.
I was
How did you come across that fact?
taught in physics.
In physics, and but you were taught simply by being told. That's what it is.
Yes,
Okay.
more or less.
How about knowing it by experience, like first-hand experience? How would you do that?
Well, everything from a plane going by overhead. The sound of the plane is behind the actual position of the plane. Or if you're far away from something like a ball bouncing on a concrete, if you're far enough away, the ball bounces, you see it up in the air, and then you hear it when it hits.
And then
and then it bounces
You
again.
know the distance to the ball.
Yeah.
And then you have a
How long
stopwatch
delay.
that counts the time between the time that you saw it hit and the time that it gets your ear.
Mhm.
What's a typical event?
Lightning and thunder.
Lightning and thunder, exactly. In elementary school, you were probably told that you can tell how far lightning is by listening to the thunder. And your teacher at the time said, well, if you look at thunder, at lightning, and you count to 5, it's a mile away. Right? You already know that. So how much is a mile? 5,000 feet.
Something.
So it's 5,000 feet away. It takes 5 seconds to get to you. Sound is traveling roughly at 1,000 feet a second. Right? And now you don't need to read it out of a book. Just remember your elementary school teacher. You remember her name? Or his name?
This is Frank Gordon.
Yeah. Very good. So the same thing you need to worry about, if you are worried about it, is you can control delay by moving the microphone away from the source of sound. For every foot, 1,000th of a second. And so you say, well, these gadgets, these sound synchronizers, you know, they must be pretty expensive. Well, yes and no. If you start out with this system, you have a flash that you want to fire, and then you say, well, I want to fire it in response to sound. Well, you need something that is going to close a switch. First of all, there's a switch in this gadget here. It's called an SCR, silicon control rectifier, or whatever that is. It's an electrode switch. It has 3 connections on it. 1, 2, and 3. And when there is power applied to these two, the gate and the cathode, okay, the cathode and the anode connect together. So you connect these two to the flash in a particular way. If it doesn't work one way, you go the other way. And then you connect these two to the earphone jack of the tape recorder, which the tape recorder, when it's recording, it does, its function is to pick up sound and modulate a magnet by which the tape moves, so that then the tape has some magnetic information on it. But it takes electricity to do that. So that part of the component of the device is a pickup or an amplifier, and then you drive the magnets. But at the same time, the tape recorder lets you monitor what you're recording, okay? Or many of them do. And if you have that, whether it's a cassette tape recorder or whether it's a movie cam or something, anything that allows you to monitor what you're recording. Say there are 2 types of microphones, so one works better than the other. But anyway, there's power coming out of here, a very minute amount of electricity, which drives your headphones. Well, you can use that to drive this part of this SCR. The SCR costs about $1. And now, that's your El Cheapo sound synchronizer. And a finished one looks like this. This fits into the earphone jack, so electricity will connect to these 2 parts. There's that SCR gadget, and here's a PC connector, okay, to which you can attach the PC connector on the flash. It connects you to the camera, or in this case it would be to the flash. The most expensive part here is probably that. And this is what it looks assembled and attached to the flash. And then, of course, this doesn't have that PC connector on it. It's been replaced by a PC socket just sitting in there. But it's the same idea. And if you want to get more complicated, in that case, you can build these with something called integrated circuits, and that's what this is. This is essentially the guts of the tape recorder, right in there. And right next to it, there is the SCR, also in a little integrated circuit. That's a little more difficult to make, but the other one is quite satisfactory. And I was planning to do a demo right here, but I ran out of time. So the demo would be something like this. Okay, so notice the position of the microphone. Farther and farthest. Now, I think the distance between the microphone here to the balloon and the microphone here to the balloon is about a foot. Okay, so this allows me to actually predict roughly the amount of time that it takes this balloon to disappear, from the time I hit it until it's gone. How do I do that? Well, I have this picture, and I have this picture. I know the time between them is 1,000th of a second, right? Because I moved the microphone a foot away. So then I take a look at this one and say, well, how much of the balloon has ripped away? How much has disappeared? And anybody want to tell me? Roughly, I'm going to deal with rough numbers. Let's say a quarter.
Quarter.
A quarter, okay?
Okay.
Now normally I would do something like this. How much of the balloon has disappeared in the first photograph?
A quarter.
And he says a quarter. Okay, so now I go, oh, Laura, I'll ask you. How much of the balloon remains in the second photograph? She says a quarter. You said a quarter, right? Sure. I'm not putting words in your mouth. All right? So, a quarter has gone, a quarter remains. Whether it's true or not, play along. A quarter has gone, a quarter remains. How much of a change was there between the two photographs? A half.
Say 1,000.
A half of the balloon changed between the two pictures, right? In how much time? So how long will it take for the whole balloon to disappear if half of it took 1,000? 500. Remember that earlier slide that said it takes the balloon a 500th of a second? You can do it this way. Now, could you use a high-speed gazillion-dollar camera to do it? Yeah. Would the results be appreciably different or significantly different? Probably not. Okay, once you do this, then you can do stuff like this. And these are the flashes that we're going to use. And this is a typical high-speed photograph. And another one, and another one. And
We can't do cans though, because there's no.
I don't know.
Okay. Sounds good.
Alrighty then.
See, this was those cans were before security.
Yeah.
So, see you all, or some of you, tomorrow. And I hope, as I said in that email, I hope you are having a great week.